Hello Calc 3, welcome back to another video. So in this video we will cover section 13.3, the second to last section for chapter 13, and it will be on arc length in space. So remember back in Calc 2, probably towards the end of Calc 2, when you gave parameterizations of curves in the plane, you developed a formula that would give you the arc length of a curve. And in this section, we're going to develop a formula for the length of a curve in space as opposed to the plane. And to do so, we simply account for the extra dimension. So we're just going to add in the fact that we have a third dimension for curves in space. So let's move on to the definition. If we have a smooth curve, which is given by r of t with component functions x of t, y of t, and z of t, then the length of the smooth curve from a to b, that is traced once as t increases from t equals a to t equals b, is given by the integral from a to b of the square root of dx dt squared plus dy dt squared plus dz dt squared. And here you can see that this is just a generalization of the formula that was developed for curves in the plane, where all we've done to change the formula is add this third component here, dz squared. But there is another way to write this formula, a little bit of a shorthand when we're talking about vector valued functions. So remember that the velocity function is given by dx dt as the I component, dy dt as the j component, and dz dt as the k component. And so if we were going to take the magnitude of the velocity function, we would get the square root of dx dt squared plus dy dt squared plus dz dt squared. And that looks very similar to our integrand. So we can rewrite the definition for the length of a curve, and this definition here is just a shorthand of writing the same thing. So L is equal to the integral from a to b of the magnitude of v of t dt. Okay, so let's move on to an example where we are finding the length of some curve. So let's say that a glider is soaring upward along the helix. R of t is equal to cosine ti plus sine tj plus tk, and we want to know how long the glider's path is from t equals 0 to t equals 2 pi. So remember, we talked about the helix in, I think, section 13.1. It's come up a couple of different times, but let's see if we can solve this problem. So we're mostly just going to apply the definition that we just set forth above. So the velocity function is going to be equal to minus sine ti plus cosine tj plus k, where we've just taken the derivative of the component functions from r. And if we take the magnitude of the function giving the velocity vector, we get the square root of negative sine t squared plus cosine t squared plus 1 squared. And then using the trig identity that sine squared of t plus cosine squared of t is equal to 1, we end up finding that the magnitude of the velocity is always going to be the square root of 2, regardless of t. And using the definition of length now, we get that the length is equal to the integral from 0 to 2 pi of radical 2 dt. And we can just pull the radical 2 out, of course. And ultimately, we end up finding that the length of the curve from t equals 0 to 2 pi is equal to 2 times the square root of 2 pi units. So if you were going to give a unit like meters or something like that to make this more of a real-world application to hang gliding, then the glider would soar 2 times the square root of 2 times pi meters as it's going around one rotation of the circle upwards on the helix. Now let's move on to a little bit of a different topic. So let's say that we have a curve, and just for the sake of simplicity, I'm going to draw a curve in the plane as opposed to a curve in space, and we'll call that curve R. So that curve is the blue curve inside of the plane that I have drawn. And we're also going to pick some arbitrary point on the curve, and we're going to call it P sub T naught, which is the point in red. So then, once we pick this point, which will be called a base point, for any other point that lies on the curve, there's some t such that that point is what pops out of our function r when we plug in t, right? So we can just represent all the other points on the curve as some ordered pair x of t, y of t, and we can give a function representing the distance along the curve from our p sub t naught to all the other points on the curve p, and that distance is going to be given by this function here, this s of t. So notice how the limits of integration go from t naught to t, so we start at the t associated with our base point, and then for all other points, we can find that t associated with the point, and then calculate the length from our base point to that other point by using the definition that we've given for length above. And we've switched out the variable t with tau in our integrand. That's nothing really special is going on there. It's just because we have the variable t as one of the limits of integration, so we've just replaced the variable for the velocity function with tau. And now if t is greater than t naught in our integral here, then this function by definition is going to give us the distance along the curve from our p sub t naught to the other point. And if t is less than t naught, then s of t is going to return a negative value, and it's actually going to give us the negative of the distance along the curve from p sub t naught to whichever point is corresponding to that t. So each value of s is going to give us a point on the curve, and ultimately this allows us to parameterize the curve with respect to the variable s as opposed to the variable t. So typically we're parameterizing a vector valued function with t, but we can parameterize with s as well, where s is giving us a distance along the curve. So we can call s the arc length parameter for the curve, and this is ultimately going to prove useful in the next section. It probably won't seem super useful for now, but let's give an official definition. So the arc length parameter with base point p of t naught is given by s of t is equal to the integral from t naught to t of the square root of x prime of tau squared plus y prime of tau squared plus z prime of tau squared d tau. And again, we can write that with some shorthand and just substitute the integrand from this equation here with the magnitude of the velocity function with respect to the variable tau. Okay. So I said previously that typically we parameterize the curve with respect to the variable t, but that this new variable s at some points will give us a way to parameterize the curve as well. And sometimes it's actually possible to calculate this new parameterization with respect to s. And to do so, let's assume that we have a curve r of t, which is given in terms of the parameter t, and at times we're going to be able to give t as a function of s. So we can write t is equal to t of s for some function t of s, and then r of t will be equal to r of t of s, where we've just substituted t for the function t of s, And once we've done this, then r is given in terms of the arc length parameter. So if we can find this function relating t to s, then we are able to write r parameterized by the arc length parameter as opposed to t. So let's give an example of when this is the case. It is certainly not always the case that we can actually calculate this, at least not easily. So let's let r be the curve cosine ti plus sine tj plus tk. So this is just the helix that we've been working with a bunch. And we want to find the arc length parameterization of the curve. Okay, so our base point is going to be the point at t naught equals 0, so that this point is ultimately equal to 1, 0, 0. And then the arc length from p of t naught to some point p of t is going to be given by s of t is equal to the integral from 0 to t of the magnitude of the velocity function with respect to tau. And after we solve this, so remember from the previous example that the magnitude of the velocity function is always going to be equal to the square root of 2, regardless of the value of tau. And we end up finding that a function giving s with respect to t is the square root of 2 times t. So s is equal to the square root of 2 times t. And using a little bit of algebra, we find that t is equal to s divided by the square root of 2. So here we have a function giving t with respect to s. And this is what we needed to give a parameterization of r with respect to s. So now r of t is going to be equal to r of s divided by the square root of 2. And of course, this is equal to cosine of s divided by the square root of 2i plus sine of s divided by the square root of 2j plus s divided by the square root of 2k. And here we've given, now we've given r as a function with respect to s as opposed to a function with respect to t. But again, typically finding a parameterization with respect to the arc length parameter is difficult, but it will come up in the next section. And now on to the last topic for section 13.3, the unit tangent vector. So we've already said before that the velocity vector for some curve is denoted v, and it's the derivative of our curve with respect to t. And we know that it's tangent to the curve at different points t. But the velocity vector has a magnitude as well as a direction. And sometimes we want to care about the direction and not care about the magnitude. And to get rid of the magnitude and replace it with a vector that is tangent to the curve, but also a unit vector, we're going to divide by the magnitude of the velocity vector. So the velocity vector divided by the magnitude of the velocity vector will give us a vector tangent to the curve, but that is also a unit vector. And we're going to call this vector the unit tangent vector. So the unit tangent vector is defined to be the velocity vector divided by the magnitude of the velocity vector. And this unit tangent vector is going to give us a nice way to characterize the direction of a particle that's moving along the curve at different times. So let's give an example of calculating the unit tangent vector. So let's say we have the curve 1 plus 3 cosine ti plus 3 sine tj plus t squared k, and we want to find the unit tangent vector of this curve. So first we're going to calculate the velocity. So the velocity is just the derivative of our curve r, and to find the derivative, we take the derivative of the component functions. We end up finding that the velocity is equal to negative 3 times sine ti plus 3 times cosine tj plus 2 times tk. And now we want the magnitude of the velocity. And so that's going to be the square root of 9 times sine squared t plus 9 times cosine squared t plus 4t squared. And again, we can use the fact that sine squared of t plus cosine squared of t is equal to 1 here. And ultimately, we find that the magnitude of the velocity vector is equal to the square root of 9 plus 4t squared. And now we just apply the definition of the unit tangent vector t. So t is going to be equal to the velocity vector divided by the magnitude of the velocity vector. And that'll be equal to this equation here, where we've just taken the velocity vector and we've multiplied through by 1 divided by the square root of 9 plus 4t squared. Okay, and the last little tidbit for section 13.3, let's look at the derivative of our curve r with respect to s as opposed to with respect to t. So we already said that we can parameterize the curve with respect to the parameter s as opposed to the parameter of t. Let's see what happens if we take the derivative of our curve with respect to s as opposed to t. So first, we want to note that the derivative of s with respect to t is equal to the derivative with respect to t of this expression here. So it's the derivative of the integral from t naught to t of the magnitude of the velocity, and that is going to equal the magnitude of the velocity at t by the fundamental theorem of calculus, which is something that we talked about, I think, in section 13.2. So the fundamental theorem of calculus allows us to say that ds dt is equal to the magnitude of v of t. And for that reason, dt ds is going to be equal to 1 over ds dt, which we just said is equal to the magnitude of the velocity. So the key here is that the derivative of t with respect to s is equal to 1 over the magnitude of the velocity. And now we're going to apply the chain rule. So the derivative of r with respect to s is equal to the derivative of r with respect to t times the derivative of t with respect to s. The derivative of r with respect to t is defined to be the velocity, and we just found out that the derivative of t with respect to s is equal to 1 divided by the magnitude of the velocity, which means that the derivative of r with respect to s is equal to the velocity over the magnitude of the velocity, which is by definition our unit tangent vector. So the derivative of r with respect to s gives us our unit tangent vector. And this is an idea that's going to show up in the next section, but this is the end of the material for this section, so look out for section 13.4.